In this example, we're going to look at how we would graph and analyze data for position and time of two different cars. As you can see on the left, we have two data tables, one for two different cars, and you see that time was measured and position was measured. We use a variable t for time and x for position. It was measured in meters. Since we chose x, you can assume that car is moving horizontally along the surface. So let's start with our first car. We'll do the first car in red, and we're just going to plot the points on our graph. So at time 0, the car is located at 1 meter. At 2, we're at 2.2, so I'm going to estimate somewhere right around here. At 4 seconds, we're at 2.9, so just under 3. At 6, we're at 3.5, halfway between 3 and 4. And at 8, we're at 5.2. So we'll go up to 5.2 right around here, right? So we see this set of data, and you might see that it appears to have a trend, a pretty constant trend up and to the right. And when we observe this car moving, it seemed to be moving at a constant speed. So let's see what happens when we actually draw a line of best fit. So when we analyze data in a science class, we're not going to ever get clean data. We're going to have little bits of error, and that error is going to be shown in this way here, where you have points that don't quite fit a line perfectly. And so what we're going to do is do what we call a line of best fit. So I'm going to put this line of best fit through the data for car 1. Right? Again, this is called a line of best fit. And we use lines of best fit to average out all the little errors that might be in the data itself. Notice those data points are not actually all on the line, but that line attempts to fit the data as best as possible. And so if we want to predict future positions of this car, we can use the line of best fit to actually analyze and make some of these predictions, even though the individual measurements we made did not all fit this line. Let's go to the second car here. We'll do the second car here in blue, and we'll put its data down. We'll color the blue car. At 0 seconds, it's located up here at 6. At 2 seconds, it's now at 4.7. At 4 seconds, it's at 2.8, so just under that dot. At 6 seconds, it's at 1.5. And at 8 seconds, it's just above 0 at 0.1. And once again, I'm going to draw a line of best fit through this data. And it looks like it starts right here about the 6. And let's fit it right in between. Maybe that looks like it fits the line. And I'll color that blue, right? So we have these two lines of best fit, one for each car. So what do we do now? Well, if I want to make predictions about this car, I now have a model for its motion with that line. And in math class, we know how to write an equation for a line. So what we're going to do here is actually analyze each line, and we're going to write a model for the motion for each car. So in order to write an equation for a line, that equation in math class is going to fit the form of y is equal to mx plus b, where y is the vertical axis, x is the horizontal axis variable, m is the slope of the line, and b is the vertical axis intercept. However, in this particular example, we don't have y and x, we have position and time. And so we look at our vertical axis, and we're going to see that our vertical axis is going to be the variable x. We're going to have a slope of that line. Now in this case, the slope is the change in position over time. And that is what we call velocity. And that is going to be the slope of the line. And we have time as our variable on the horizontal axis. And our position at time 0, we call our initial position. And so we actually have a new equation for these lines that are going to have the variables that we have in this particular problem. So we have that we can model each of these lines with an equation that says the location of the object, x, is going to be equal to its velocity times the time it's traveling plus whatever position it started at. So now let's look at car 1 and start to analyze this data. if we're going to find the slope or the velocity, we need to find 2 points on the line. I'll pick a little green pen here, and let's choose this point's on the line. Now notice, for the red car, none of the actual data points are on the line, right? They're slightly off. If I were to pick one of these other points, my slope would actually be steeper than it would if I picked a point that was actually on the line. So in this case, we actually will not use the data other than this first data point. We're going to have to pick another point on the line. So I'm just going to pick this point right here. And when you graph and use grid lines, it's a lot easier to see those points. This data point is a time of 0 and a position of 1. And this data point is a time of 6 and a position of 4 on our grid. And so if I want the slope for our red trial, this is our slope, which is going to be our velocity. We're going to want to find the change in the position, our delta x, over the change in the time. And it looks like my position goes from 1 to 4, right? This is my second position minus my first position over my second time minus my first time, right? And again, I go from a position of 1 to 4. So my second position is 4 meters minus 1 meter. And my time, I go from 0 all the way to 6. So 6 seconds minus 0 seconds. So I end up with 3 meters in 6 seconds. And I can simplify that to be 0.5 meters per second. And that is the velocity of the red line. And the next piece we need would be my starting position. My initial position for this is my vertical axis intercept is going to be 1 meter. And so my equation for my car 1 looks like this. Car 1's position, x, is equal to car 1's velocity, positive 0.5 meters per second, times the time, plus its starting position. So we've now modeled the motion of car 1. Well, let's do the same for car 2. Car 2, let's pick 2 points on that line. And if I'm zooming in here, I see that I have 1 point I can use is right here. This is a point of 0,6. And once again, none of the data perfectly fits on that line. Some are close, but let's pick a couple that are one that's actually on it. It looks like right here we can use this point that is 4,3, a time of 4 seconds, a position of 3. All right, so if I find the velocity of the blue line, I'll use those 2 points. So I'm going to find my change in position. I go from my second position of 3. This is going to be position 2 minus position 1 over time 2 minus time 1. Notice this is just our slope formula. The second position is at 3 meters. The first position was at 6 meters. My time, my second time is 4 seconds minus 0 seconds, and I get negative 3 meters over 4 seconds, or negative 0.75 meters per second. All right, so why is that negative there? Well, it's a negative slope, and this car is actually moving in the negative direction. And what's my starting position for the blue car? Well, it starts at positive 6 meters. And so we can write an equation for car 2. And that equation is going to fit the form that its position is equal to its velocity, negative 0.75 meters per second, times time, plus 6. So we now have an equation to model each car's motion. And we have the red car starting at 1, the blue car starting at 6. And we can use these equations to predict any future point. So for example, if I have the red car and I want to figure out where it's going to be at 6 seconds, I can put in 6 for t. 6 times 1/2 is 3. 3 plus 1 is 4. And it should be at a location of 4. And sure enough, that is one of my data points. 6 comma 4 is one data point. When time is 6, my position is 4. And we can expand that. If I wanted to go to 10 seconds, I can put 10 in for t. 10 times 0.5 is 5, plus 1 is 6. So at 10 seconds, the car should be at a position of 6. And sure enough, if I were to continue this line, 6 right here would be right around where 10 would be on our graph, if you could follow my cursor. All right, so here we see the power of using these models to predict where these cars are going to be. Now, let's take it one step further. What if these cars actually started at the same time, on the same track? They would collide, they would run into each other. Well, on the graph, where does that occur? Well, there is only one position where these cars would be at the same location at the same time. Sure enough, these cars, if car 1 started at the 1 meter mark, moving at its speed, and car 2 started at the 6 meter mark, moving at its speed in the other direction, they would appear to collide 4 seconds later at a location of 3 meters. So here we can use graphing to find when 2 cars will be at the same position and time on our graph. And there's a way to do it mathematically. We'll revisit that with a system of equations. But just want to kind of touch on some of these items. What else do we know about car 1 and car 2? What if they were actually in a race and they started at the same position? Well, which is the fastest car? And this is the idea between speed and velocity. Well, car 2 has a speed of 0.75 meters per second. And why is it negative? Well, it happens to be going in the negative direction. Whereas car 1 is a positive velocity. It has less speed though, it's only 0.5 meters per second. So in 1 second, it would travel a half a meter. In 1 second, car 2 would travel 3/4 of a meter. So if I'm in a race head to head, I want to be car 2. Car 2 would win that race because it has a greater speed. And we would see that the blue line is a steeper slope than the red line. Hard to see on the graph. When we calculate it, it's clear that that's the case. However, the blue line is negative only because the car is moving towards negative positions. If the blue car kept going, it would actually cross over the origin and move into negative locations along this axis. So hopefully this helps. We, again, can make predictions about where these cars are now with these models. These two models for car 1 and car 2 are just linear equations with a slope and an intercept. So we need to understand that when we have a position and time graph, the slope is our velocity. And this b value in math class is now where the car was at a time of 0, also known as the starting position.